Hello, I am Dr. Sandeep Varpe. Today we are discussing about the concept of quantum mechanics. In the quantum mechanics, the basic terminology is de Broglie's hypothesis. Louis de Broglie hypothesis of matter waves in 1924 laid the foundation on which Schrödinger, Heisenberg, and other scientists developed the quantum mechanics. This quantum mechanics are too much different than classical mechanics. In classical mechanics, we are thinking about macroscopic bodies and microscopic particles. While when you are going to atomic system, this classical mechanics is not useful. So new terminology is come forward, which is quantum mechanics. And in quantum mechanics, de Broglie's hypothesis very important thing, which give the relation, or we can say which gives the wave nature and particle nature in same equation. According to de Broglie's concept, a moving particle always has a wave associated with it, and wave is associated with a moving particle. A matter particle of mass m moving with velocity v has wave associated with it. This wave is called de Broglie wave or matter waves. Its wavelength lambda is given by the equation lambda is equal to h upon p, where lambda is the wavelength of wave and p is the momentum and h is Planck constant. If you observe carefully this equation, this lambda gives the wave nature while p gives the particle nature. So within a single equation, we are showing wave nature as well as particle nature in the same equation. This is the beauty of quantum mechanics. Next, we can obtain this equation by considering radiation. For that purpose, let's consider the expression of wavelength of matter wave or de Broglie's wave can be obtained by the analogy of behavior of radiation with a matter, in which firstly we are taking the equation which is Planck equation. So Planck equation gives the energy of photon, which is E is equal to h nu, where E is the energy of photon, h is Planck constant, and nu is the frequency of radiation. Now, next is Einstein's mass energy relation, which is a very famous equation, E is equal to mc square. Suppose this equation number 2 and this E is equal to h nu is equation number 1. If you observe these equation 1 and equation 2, both equations are related to energy. These equation 1 gives the energy of photon, while equation number 2 gives the energy with respect to the mass. So by comparing these two equations, so from equation 1 and 2, we can write h nu is equal to mc square, where h is Planck constant, nu is the frequency, m is the mass, and c is the velocity of light. Where these m into c square, we can split this c square into m into c, and this m into c we can write as a momentum. If p is the momentum of photon, then we can write p is equal to m into c. And in previous equation, we have h nu is equal to mc square. So that mc square is split into mc into c. So instead of that mc square, we can write p into c. So equation number 3 we can write as h nu is equal to p into c, where c is the speed of light. By the general equation, velocity is equal to frequency into wavelength, we can write this equation as h nu p into nu into lambda, where this nu into lambda we are putting instead of c. The velocity is equal to frequency into wavelength. If you observe this equation, in both sides there is nu. So this nu and these new, if we cancel, we are getting the new equation, which is h is equal to p into lambda. This h is the Planck constant, which gives p into lambda. If you just rearrange these equations in terms of lambda, then we get lambda is equal to h upon p. This equation gives the de Broglie wavelength of matter wave or de Broglie's wave. Now, these de Broglie wave we can write in different forms. For example, in terms of kinetic energy, accelerative potential, or rest mass. First, we'll see these de Broglie wave in terms of kinetic energy. For that purpose, consider particle of mass m moving with velocity v. Its momentum is p, which is equal to m into v, and the de Broglie's wavelength of matter wave associated with it is, we can write as lambda is equal to h upon p, which is also equal to h upon mv. This mv is nothing but the momentum. P we can write as mass into velocity. Next, the kinetic energy of particle is, we already know, which is E is equal to half mv square. In these equation, half mv square, we have to write these in terms of momentum. So we have to adjust here p square. For that purpose, we multiply this side by m and also divide by m. So it gives E is equal to half m into mv square. So this m square v square is nothing but p square. So that equation we can write as E is equal to p square upon 2m. We can write this equation in terms of momentum. So it gives p square is equal to 2mv. When we want only momentum, we have to take its square root. Square root of, if you take square root of both sides, we can write p is equal to under root 2me, where m is mass of particle and E is kinetic energy of that particle. Now this simplified form of momentum we can put in the equation of de Broglie's wave, which gives lambda is equal to h upon under root 2mv. This is de Broglie wave in terms of kinetic energy. Similarly, we can obtain different forms of de Broglie wave. For example, in accelerating potential, in that time only this energy will changes by putting the value of potential into charge. So it becomes lambda is equal to h upon under root 2mv. Today we'll stop here. Thank you.